an application that very important of the force on the current carrying wire is that when we make the wire to be a loop like this figure, okay, and we place this current carrying loop in the magnetic field, the magnetic force will produce a torque, and a torque will try to rotate the current loop. And this is the basic principle of the electric motor. That is, if you apply the current into a wire loop and put it in the magnetic field, you can rotate this wire loop from the magnetic force. Okay, so we will study here what is the torque that produced by the magnetic force when we put the wire loop in the magnetic field. This is quite simple. If we look at the simple case that we put the wire loop like this, and the plane of the wire loop parallel to the magnetic field like this. Okay. From the direction of the current, you can see that the current is in the counterclockwise direction. Okay, and if we look at the Y segment of segment number 1 here, you can see that the direction of the current is opposite to the direction of the magnetic field. So in this part, we have that theta is equal to pi, or 180 degree, and we know that sine pi is 0. So from the formula that we have discussed before, that F is equal to I L cross B, or if you write it in the magnitude of F is I L B sine theta, you can see that sine of pi is 0, right? Sine of pi is 0. So it means that there is no magnetic force on this segment of the Y. Also, at the segment number 3, because the I point in the same direction as B. Okay, so in this part, theta is equal to 0, and sine 0 is 0. So there is no force on the part number 1 and part number 3. For the part number 2 and part number 4, you can see that the direction of I is perpendicular to the direction of B. So for the part number 4, we have that F2 is equal to ILB, because sine 0 is 1. Oh, sorry, sine pi over 2 or 90 degrees is 1. Right? Also, F4 is equal to ILB2. Okay. So if we look at this in this direction, I mean we look through this direction, okay, you will see that the current on this segment number 2 is point outward, right? And the current in the segment number 4 is point inward. So when we use the right hand rule, okay, the direction of the current point along your forefinger, and the direction of the magnetic field point out from your palm. Your thumb will point upward. So we have the F2 point upward like this. And for the F4, again, the current point inward, the magnetic field point to the right. So we have the magnetic force point downward like this. Okay. So we have the couple force, and this couple force, you can see that the net force is 0 because the F2 and F4 have the same magnitude, point in the opposite direction. So the net force is 0, but this couple force will rotate, okay, the Y around the center. So we have the axis of rotation is at point O, which is the center, in the middle of this line segment. We have the length of B/2. Okay, so from this we will have that the torque from F2 is equal to F2B/2. Okay, and the torque from F4 is equal to F4B/2. Okay, but we know that F4 and F2 have the same magnitude. We may write F4 equal to F2. The magnitude of F4 and F2 is I equal, and we write that F which equal to ILB. So the net torque, the total torque, is the sum of torque to gamma 2 and gamma 4. This is the net torque. So this equal to gamma 2 and gamma 4, which is the net torque. And when we sum this is a FB/2, this FB/2. So when we sum these two terms, we get FB, which is equal to F equal to ILB. But in this case, you can see that L is equal to A. A is the length of this line segment. So we have that this is ILB times B. This B is the magnetic field, but this B is the length of this segment. Okay, and L is equal to A. So we have this IAB. Okay, and if we rearrange this, we have this IABB. This is the capital B. This is small b. You can see that this A times B is the area of this loop. A times B is the area of this loop. So we can finally write this as IAB. Okay, IAB. A is the area of this loop, and this is the magnetic field. I is the current in this loop. So this is the value of the torque when we place the plane of the loop parallel to the magnetic field. And we can see that this is the maximum torque. This is the maximum torque on the loop. Okay, because if the plane of the loop is not parallel to the magnetic field, we will have this situation. Okay. Now, if the plane of the loop is not parallel to B, okay, we still have the torque. Okay, the magnetic force are the same. F2 and F4 are the same, but now the distance perpendicular from the axis of rotation to the point that perpendicular to the direction of the force, like this. If you draw a dashed line here to the point that, if we draw the line from the that parallel to the force F2 and intersect with this line at this point, and this perpendicular to F2. Okay, we have this distance now as a B/2 sine theta. Okay, when theta is the angle, okay, this is this angle. Okay, it is the angle that the plane of the loop, angle between the plane of the loop and the force, the direction of the force, the magnetic force. Okay, so this is the angle theta. We can also write the angle theta by we define a vector. We will talk about this later soon. This vector soon. We define a vector that perpendicular to the plane of the loop as A, like this, and the direction of A is follow the right hand rule. That is, if you curl your forefinger in the direction of the current, your thumb will point in the direction of A, or A will point in the direction of your thumb. Okay. So if we define the vector A like this angle is the angle of the vector A with respect to the direction of the magnetic field, or it's the angle between the vector A and the magnetic field. Okay. Now, the total torque again is the sum of the torque from the force F2 and force F4. And when we sum this up, and we know that the magnitude of F2 and F4 are same, so we must have the total torque is equal to FB sine theta. Again, F is IAB. Okay, and when we substitute F equal to IAB to this term, okay, so we have this as IAB sine theta. This A is area, is the area of the loop. Okay, so we have the total torque is equal to IAB sine theta. Okay, and now theta is less than pi over 2, so sine theta is less than 1. This is why I say that when the plane are parallel to B, we will get the maximum torque, because in this case we have theta equal to 0. Oh, sorry, theta equal to pi over 2. The plane is parallel to the magnetic field, but the angle theta, which is the angle of the vector A and the magnetic field, is pi over 2, and sine pi over 2 is 1. So we have the maximum torque when the plane of the loop parallel to the magnetic field. In this case, we have the torque IAB times this factor sine theta. Okay. And when we look at this formula, we can see that we can write the torque in the vector form as IAB IA cross B. Okay, and now we can have the physical meaning of the vector A. We can see that from this formula, torque is equal to IA cross B. A, and if we compare with this term, you can see that magnitude of A is equal to this A. Magnitude of this vector A is equal to A, which is the area of the loop. So we may write that A is a area vector. That is this a vector that has the magnitude equal to the area of the loop and point perpendicular to the plane of the loop in the direction follow the right hand loop. That is, if you curl your forefinger follow the direction of the current, your thumb, the vector A will point in the direction of your thumb. Maybe we can see this easily in this figure. Okay, you have a current loop like this, and you curl your forefinger in the direction of the current loop. You can see that the thumb point up like this, and A point in the same direction of your thumb. Okay. The magnitude of A is the area of the loop. So we can write that the torque is equal to IA cos B. It is interesting that in this figure, if you find the direction of A cos B, okay, you can see that the A cos B will point inward. Okay, in point inward. And if you use the right hand rule, that is, you point your thumb inward into the plane of the screen or of the paper, and curl your forefinger. This is the direction of the rotation that produced by the torque. You can see that you have the force F2 point in this direction, force F4 point in this direction. So these two forces try to rotate the plane clockwise, like this. If you point your thumb inward in this direction and curl your forefinger, you can see that your forefinger will curl in this direction also. So the direction of the torque is the direction of the forefinger, the direction at that the torque try to rotate the while loop. Okay. Now we can go a little bit further by define a vector called magnetic dipole moment, which is, we write it as a mu. This vector will be very important when you discuss about the dipole moment of the atom, or the dipole moment of the some kind of antenna, or dipole moment in the atom. Okay. Anyway, in this case, we will define mu as I times A. I is the current, A is the area vector. So you can see that the magnetic dipole moment will point in the same direction as A. Okay, you can use the right hand rule to find the direction of mu, and the magnitude of mu is equal to IA. Okay. From this definition, we can write the torque equal to mu cross B. Okay, we can write the torque as a mu cross B, and we can also define the potential energy, that potential energy of the magnetic dipole as the U equal to minus mu dot B. I will not derive this formula, but you can see the this is reasonable definition. Okay, you can see that from this definition, if you point if mu point in the same direction of B, you will have the minimum value, and if mu point in the opposite direction of B, you will have the maximum value. Because if we have mu point, we have mu point in this direction, and we have B point in this direction. If mu point in this direction, from your right hand rule, you can see that if you look at the while loop, you have that the current in this portion point in, the current in this portion point out, right? Okay, and from the right hand rule again, you can see that if you want to calculate the magnetic force in this segment. Okay, you can use the right hand rule for the magnetic force. And the magnetic force, okay, let me change this figure a little bit. Let me tilt the loop a little bit. In fact, you can have the loop that perpendicular to the magnetic field, but in that configuration, the loop will be in the unstable equilibrium. So maybe it's a little bit harder to explain. So let me tilt the loop a little bit. Okay, but the magnetic dipole point in the opposite direction of B, and if you calculate the magnetic force, okay, if you calculate the magnetic force, your forefinger for this segment, your forefinger point inward, and the magnetic field point out from your palm. So you will have that the magnetic force point in this direction. Okay. And if you look at this segment, okay, your forefinger point out, and your the magnetic field point out of your palm, right? You will have the magnetic force point in this direction. Okay. Okay, something like this. So it means that the magnetic force try to rotate the current loop in this direction, and we know with this is naturally that the system try to change from the state with a higher potential to the lower potential. So it means that if we let the Y can rotate freely, it will rotate in this clockwise direction. So the state of the Y loop here is in the higher potential, and it try to change the configuration to the lower potential. Okay. Now let's see what will happen in the opposite direction. That is, now if you have the current loop, but now the current point in this direction. Okay, in the first case, the current point in this direction, this is I. Now the current point in this direction I. B point in the same direction. Now you can see that from the right hand loop, okay, we have the magnetic dipole moment point in this direction. Okay, magnetic dipole moment point in this direction. And if we calculate the magnetic force, in this segment, okay, forefinger point out of the plane, B point out of your palm. Okay, you will have the magnetic force as point in this direction, FB, right? And here is point in this direction, FB. Okay, from this segment, you can see that if your forefinger point out, okay, and the magnetic field point out of your palm, so you have the magnetic force like this. Again, you can see that this magnetic force try to rotate the plane into this direction. So it try to, you can see from these two examples that the magnetic force will try to rotate the magnetic dipole moment vector to align with the magnetic field. In this case, you can see that the loop will try to rotate clockwise like this, but in this case, the loop, the magnetic force or the torque will try to rotate anti-clockwise like this to make mu point in the same direction of B. So it means that when mu point in the same direction of B, the potential energy is lowest. Okay, and this is reasonable because in this case, the angle between mu and B, I may write it as a phi. This phi is small. Okay, this phi is small, and we know that cos theta is of small angle is approximately equal to 1. So from this relation, we have that this equal to the minus mu b cos theta. Okay, so it means that when this in this case it's phi. So when phi is small, cos theta is approximately equal to 1. So u is equal to minus ub. But in this case, you can see that phi is approximately equal to pi, right? And we know that cos pi is equal to minus 1. So in this case, u is equal to mu b. This case, u is equal to minus mu b. So this is the maximum potential. This is the minimum potential, which is agreed if we look at the direction of the rotation that the torque try to rotate the loop. Okay. And from this, when the torque try to rotate the loop, that we can apply to the electric motor. Okay. In this definition, we define the magnetic dipole for a single current loop. In general, when we have the N loop, we may write that mu is equal to N I A, because every single loop we will experience the torque from the magnetic force, and for the total torque is the sum of the torque of every loop, which is now the N time of the torque of the one loop.